All right, let's talk about automatic exposure control, portables, and tomography, not to be confused with computed tomography. All right, so we're going to talk mostly about AEC usage, how to use these things. You're using them every day. No one knows how to use them. They're all doing it wrong. Then we're going to demonstrate how to use these density controls because they're really whack. They don't make any sense the way that they're put together. There's limitations to these things. So we're going to talk about what those limitations are. And then we're going to talk about portables. And then we're going to talk about tomography. Tomography is the one thing I don't think it was in our reading. And there's not a lot that you need to know about. There's only one clinical site that's currently using tomography. And honestly, I'm not that interested in it anyways. But we do need to at least touch on it. All right. When we're talking about automatic exposure control, the first thing that we need to think about is, well, what the heck is an automatic exposure control? So looking in our textbook on page 411, we've already illustrated what the basic circuitry is of this doohickey, right? It is an ionization chamber that's positioned between the patient and the image receptor. And as X-rays pass through the patient and exit the patient, they strike this ionization chamber, and if enough ionization occurs, it terminates the exposure. So we can use it instead of mass. We can just set an MA and a KVP and set the time based off of when we've got an appropriate exposure for the area of interest. So how does it do that? It talks about it starting on the bottom of page 411. An electrical charge is induced. The current is stored in a capacitor until it reaches a threshold that corresponds with an ideal amount of radiation exposure, right? Then the thyrotron in the circuit releases the charge in a surge of electricity that activates the electromagnet and cuts off the exposure. That is an automatic exposure control.
The thyrotron is pretty much what flips the off switch. Correct.
The thyrotron is what initiates that off switch. It's like the robotic hand that cuts it off, right? All the automatic exposure control controls is time. It does not control MA, and it does not control KVP, and it does not control your patient positioning. So if you didn't do any one of those three things right, the AEC is going to start to work against you. That's why we need to talk about it, right? So in thinking about those things, when we talk about KVP, what we should understand is that no amount of exposure compensates for inadequate penetration or quality. So we need to have an appropriate KVP for the position that we're shooting. That's why oftentimes if I ask you in simulation what technique would you use for that, all you need to tell me is a KVP, because I'm assuming the rest of it is done with an AEC. Right? As long as you know what's going to provide sufficient penetration for the exposure, I'm saying we're good. And if you're wondering where this is in the textbook, on page 412, middle of the page on the left column, no amount of exposure can compensate for inadequate penetration. That should have just been the name of this textbook because he says it like 50 times. So it's important. All right. The MA. The MA needs to be high enough to minimize motion, but not so high that exposure times are shorter than the minimum response time, the MRT. What is this minimum response time? Well, all electrical equipments, I have an iPhone 5, state of the art. For me to push the button on the screen and it to do something is its minimum response time. It has a little hang time, and I can sense it. Like if I push the button and well, it's not doing anything now, but if I swipe across the screen,
Impressive.
Yeah, I'm pretty happy with this one. All electronic devices have a minimum response time. It requires them a little bit of time to wake up before they initiate whatever they're doing. And that's true with the automatic exposure control system as well. It needs a little bit of wake-up time. It may be a fraction of a second, but it needs a little bit of a wake-up time. So if I set an MA that's too high, I could wind up overexposing the patient because it's going faster. It's exposing faster than that minimum response time, that hang time. So that's a problem, right? Knowing what that minimum response time is for the system, and unfortunately they vary a whole lot, right? Anywhere from 0.002 seconds to 0.02 seconds. So in general, use an appropriate MA. Most machines are already set for that. So that's not a big concern, but it's something that's out there and something to be aware of.
So you don't want your minimum response time?
Okay, so good, thank you for saying that. The MA is controlling the exposure. So the higher that MA is, the more rapidly the patient's being exposed. If I'm exposing the patient so quickly that the machine didn't have a chance to cut off, I've overexposed the patient. That's exceeding the minimum response time. The MA was so high that I was exposing the patient too quickly for the machine to shut off. He talks about this on page 412. He says at the bottom of the column on the left, it takes time, albeit thousandths of a second, for the circuit to detect and react to the radiation received. In English, what he's saying is, don't expose it faster than what it can take. Don't expose it faster than what it can take. So that's on one end of the spectrum. There is something on the other end of the spectrum, and that's called the backup timer. There's a backup timer as well. And so this is talked about on bottom of page 412 moving over. A backup time or backup mass must be set to prevent excessive duration of the exposure in this event. So it's possible the AEC circuit could fail, or you could screw up and not position the patient correctly, right? So the backup timer should terminate the exposure, so you're not just sitting there frying the patient waiting for the AEC to turn off, right? That's the backup timer. Generally, if we look middle of the page on page 413, column on the left, generally the backup timer should never be more than 2 times the expected exposure time or the mass of a particular projection. The reason I'm stressing this one in particular is right out of the box, a lot of the machines that you're working on have their backup timer set too high. It needs to go, the technologists have to go in and manually reset the backup timer. And knowing some of the knuckleheads that y'all work with, they probably didn't do that, right? Like there was egg rolls in the cafeteria that day or something, right? So this is in your work description as a technologist to know what the backup time is set anytime you're using the AEC, and to know how that relates to the expected mass. If it's anything more than 2 times the needed mass for that projection, it needs to be manually changed. It needs to be manually changed. Another thing that can happen if we're using this and we can hit the backup timer is if we didn't activate the right ionization chamber. So we see that bottom of this column on the left, a common error while using the AEC is to forget to activate the correct Bucky mechanism, right? Yes?
Is the backup timer like, is it automatic or is it like a button?
It is a time that's set in the machine.
It overpasses.
And if it hits that time, it says, you're out of time.
Okay.
So it might be 2 seconds. Generally, it's about 2 seconds, 2 to 4 seconds. 4 seconds for most stuff is like irradiating the patient 5 times more than they need to. There's no reason why a backup timer needs to be 4 seconds for most of what we do, right? There may be rare exceptions to that, right? But if you think about 4 seconds, that's a long time. Beep. I mean, that's like a Jerry Springer level cuss out. You know what I mean? So 2 times is normally best. So if we didn't have that set up, though, right, what would happen is we'd have the patient, maybe we didn't activate the right bucky, maybe we activated the table bucky instead of the wall bucky, and we're doing a chest x-ray, right? So we're holding our finger on the button, it's going beep again, and it's not cutting off, and we're like, wow, this patient must be made out of titanium or something, right? Then it hits the backup timer and it cuts it off, right? Now here's the deep irony, right? When it comes to digital imaging, those pictures are going to look exactly the same. The one that was appropriately exposed is going to look exactly like the one that was fried 500 times over. I'm not joking, because I've actually done experiments even in this old system here with the Fuji where I did just hand x-rays. I did hand x-ray on the film system, and then I did hand x-ray on the digital because we used to have film. A dose that would have irradiated the patient 500 times over. We could have gotten 500 hand x-rays. If we did that on the digital system, you still got a pretty picture. So we'll be talking a lot about that, but that's what we're talking about with the backup timer. It's there to prevent that, to prevent overexposure. All right, the other kind of woolly thing that comes with messing around with automatic exposure controls is to think about density control. But before I jump into this, I want to point one thing out, because there's a major statement that he makes on page 414, and I don't want us to get past this. Back in the day of film, right, the main reason you got paid the big bucks was twofold. The main reason you got paid the big bucks was knowing how to limit occupational and patient exposure, right, and knowing how to make a complicated film picture. The pictures were very, very tricky to make. They required a knowledge of chemistry. They required a knowledge of radiation exposure. You need to know your techniques really, really well, you know. You had to sit and do technique calculations constantly to get a good picture. You could very easily overexpose or underexpose and get a crappy picture, and you'd have to go reshoot it. So that's no longer the case. Digital has pretty much solved a lot of those problems, and it continues to solve a lot of those technical problems of overexposure and underexposure. Digital, we're relying on the digital system to do a lot of that. Your main job now is for us to be involved in the risk of your patient, right, and to advocate for their interests as we're using radiation. Your main job title switched when we switched over to digital to primary relief. It's no longer the technical part. It's more reducing patient dose, optimizing patient dose, informing patients about their radiation dose, those types of things. Okay. So just below that, he indicates on page 414, backup times of 2 to 4 times the expected exposure should cover nearly all contingencies, right? So if we ever see a backup timer higher than that, we need to manually change that. No questions asked. You don't need to call your manager and ask them, hey, can I change the backup timer? No, just do it, because you're the tech, and the buck should stop there. All right. Let's talk about this little knob or this little button that changes the density control. It's sometimes a little plus or a little negative sign, and you'll see the technologist punch it before or after, generally before making an exposure, right? I think I'm going to bump up the density on this, right? Normally it's indicated as density. It will be found on the console, and this applies to the AEC circuit, right? Well, what is it doing, right? It is changing, remember the robotic hand, the thyrotron? It's changing how quickly or how slowly the thyrotron moves. So as I bump up the thyrotron, the hand moves slower. As I bump down the thyrotron, the hand moves quicker, right? So I'm going to get a lighter image or a darker image, depending on how I've set it. And density, just so you know, this term we might as well go ahead and define it. Density refers to the overall darkening of the image, right? The overall darkening of the image. So the blackness of the image is what we're talking about when we talk about density. So If I bump it up, the image will be more dark. If I bump it down, the image will be lighter. It will be less penetrated. It will be less exposure, yes.
And that's in the anatomy?
In the anatomy of interest, yes. Good question. In general, these density controls represent a 25% change, right? Not particularly helpful, and we'll talk about why that's the case a little bit more in the spring, but in general, we need at least a 30 to 35% change in mass to see a difference in the image, right? So what that means is if we're going to bump the density up, we need to bump it up twice. That will create an actual change in the density of the image, right? If we need to bump it down, we only need to bump it down one. So this is a really, really rock solid rule of thumb that works on almost every system I've ever worked on. That if you're going to bump it up twice. If you're going to bump it down once.
So if you bump it up twice, you're going to make it darker.
Correct. You bump it up twice, the image is going to be darker. Bump it down once, the image will be appreciably lighter. The exposure indicator will indicate that it is less exposed. Now sometimes, since we're talking about density, we're talking about it as darkness or blackness on the image, there is a flip side that we sometimes talk about in digital, and we'll come back to it here in just a minute, but we may refer to brightness, right? Brightness is actually something we can measure as well with the digital system. So brightness on radiography refers to underexposure. Brightness refers to underexposure. So density refers to darkness or exposure. Brightness refers to something that's unexposed. So bones appear bright because there's decreased exposure wherever bones are because of their mineral density and their thickness.
Can you say that again? Density refers to?
Blackness. Brightness refers to whiteness. Now, he talks about this on this image here. You can see what we're talking about. We've got a targeting system, right? And they've placed the target. It doesn't look like the target was quite placed over the area of interest. So here's the indicating where the ionization chamber was located on this exposure of a frog leg lateral hip. Now, it doesn't matter. I don't think we've quite covered frog leg lateral hips. But just know we should be centered on the joint. We are not centered on the joint. The technologist has centered on the shaft of the femur, right? Since they were not centered on the joint, I can't frickin' see the joint. The joint is where that black arrow is, right? So it is crucial that we are targeting the AEC in what I would call the anatomy of interest. The anatomy of interest is what should be at my targets. Okay, so let's talk a little bit about that. So poor patient centering can result in over or underexposure of the image receptor, right? So in this case, let's look at this picture again on page 415, right? Figure 27.2. This, I've said, was uncentered for this frog leg lateral. We centered it on the shaft of the femur instead of on the acetabulum of the pelvis, right? What happened on this? How would we describe this image? Is it too light or is it too dark? It is too light. It is too bright of an image. So is it overexposed or is it underexposed? Underexposed. Good. Good. So what this means in the world of the AEC is it cut off too soon. It cut off before it had adequate penetration. We didn't get enough exposure, enough density in the area or the anatomy of interest. So it cut off too soon. That's what a picture looks like, on film at least, if it cuts off too soon. Well, let's look at this other image here up above it. We have an off-centering of, it looks like a lumbar spine maybe, right? The lumbar spine wasn't centered for this image over the photocell. So the photocell is partially uncovered. How would we expect this radiograph to appear?
What figure?
Just above it, figure 27.1, the lumbar spine. How would we expect this X-ray to appear if we don't have the lumbar spine over the ionization chamber?
Would it be the same?
Correct. It'd be exactly the same. It would be underexposed. So we can see there's a number of ways we can screw this up, right? We can just not be centered on the anatomy of interest. We could have the anatomy of it. We could have the wrong photocell activated, that type of thing. All of those things generally are tied to underexposure.
Is this mostly due to poor positioning?
Poor positioning, patient discomfort, inappropriate use of the AEC itself. So I would question the AEC's use on a frog leg lateral anytime. I don't think you need an AEC for that projection. You definitely, for example, you don't need an AEC for an elbow, for a wrist, for a hand. Because think about it, there's no way that my hand can cover all of that ionization chamber, right? So it's not helping me there. Also, the technique is so low, I'm fighting the minimum response time. So the anatomy needs to completely cover at least one detector cell. The anatomy of interest needs to completely cover at least one detective cell. So we need to take a special care anytime we're imaging anatomy on the margins of the body, like a clavicle. Clavicle, it's going to be really hard to get a good AEC technique on a clavicle. Why? Because part of the photocell is going to be poking up over the patient's shoulder, right? So we see that on page 417. Crappy use of an AEC results in underexposure to a clavicle of all things. Like this should be, there's no reason we would ever need a AEC on a clavicle. We just need to know what the clavicle technique is. So it's here to help you, but there's some limitations to it. And so those are stipulated here on page 416 and 417 of the textbook. And I've put them in, I've shortened them here and placed them on this, this slide for us in a shortened form. But basically, make sure you center appropriately, make sure that the anatomy covers the AEC cell completely, make sure that it's not on the periphery of the body. Even if the AEC is used properly, make sure that it's representative of the anatomy of interest and ideally the tissue of interest, right? And he talks about that distinction on number 3. The X-ray field needs to be collimated appropriately, because what happens when we don't collimate well? What do we increase when we have collimation too big? Scatter. And so scatter is another thing that could reach the AEC and change it, right? So if we have a whole bunch of scatter here hitting the ionization chamber, it cuts off the exposure too soon. So now we've got a picture that's too light, plus the subject contrast is crap, right? So collimate appropriately when you're using an AEC. Y'all are so smart. Y'all got this.
Until we get to your test.
Just keep punching me in the kidneys over and over again. All right. And anytime the patient has hardware, or they've drank barium, or they've swallowed a bunch of Barbie dolls, or they've placed something in their rectum, you do not need to use an AEC. So if there's any suspicion of metal, surgical hardware, anything in that area of interest, what's going to happen? Okay, so hypothetical question. Patient comes into the emergency department with a flashlight in their rectum, right? We use the AEC center photocell on their KUB. How is the image going to appear? Is it? What's the metal going to do? What's the metal going to do, Ms. Ryan? Is it going to attenuate more X-rays or less X-rays than what is normally in that anatomy? It's going to attenuate more X-rays, and if it's situated over the photocell, If the flashlight's over the photocell, what's going to happen to the rest of the picture? It's going to get darker and darker and darker, because if you can imagine, the exposure time you're going to have is beep, oh my crap, what's in his rectum, right? Like, because the metal in that flashlight is sitting over the photocell, and it's attenuating all those x-rays that should be getting to the photocell and terminating the exposure. So any kind of metal hardware in the area that an AEC is being used is going to wind up in an overexposure. That's a really crass example, but it serves the purpose.
So if you don't use an AEC, what do you use? You have to set your own technique?
You got to go back to technique charts. Yep, you got to go to manual technique. Now you'll find there are some facilities, there was one facility I worked at where for whatever reason the AEC worked great on AP lumbar spines, but it was crappy on the lateral, right? So we always had to set manual techniques on the lateral. So what we would do is we would watch what the AEC did on the AP, and we would set the lateral technique based on the AP, right? So you can kind of frog hop off of one technique to the next. So here's what I got on this one. But be aware, if you see a machine that's consistently shooting low or consistently shooting high, something's going on with the AEC 9 times out of 10. And it's one of those things that's kind of out of sight, out of mind. That's why I'm stressing it. This is probably one of the only times people will talk about it at this depth. We'll come back to it again in the spring because this is important. Because it's one of those things that's out of sight, out of mind. Techs don't always think about it. But it's significant. It's a big part. All right. Ports, and then Tomo Technique, and then we'll be done. So for talking about portables, we'll be done with this chapter at least. I'm switching over to 671. Page 671 is where we start talking about portables. So portable technique is a little bit different from the techniques that we use in the department because portables are pretty much direct current. They don't have to worry about rectification or any of that kind of stuff. And it was particularly noticeable back in the day, but it still affects things. It still affects techniques. So you cannot use a technique from the department on your portable machine. That's the big takeaway for this discussion of portables. Portables require their own technique. Every portable machine needs its own technique chart. And the reason I'm beating that drum is because a lot of facilities simply don't have them, right? So I don't know that technologists understand this at some of the clinical sites that y'all are going to. So, although a lot of different generators exist, nearly all mobile X-ray units now use what's called constant potential generators, CPGs, constant potential generators. Back in the day, we also had falling load generators, which is what that Siemens machine is that we have in the lab. It's a falling load generator. You plug it into the wall, and it charges up a capacitor, and the exposure is made in a falling capacity. So it exposes a little bit more, and it starts to fall off as the exposure prolongs. But these new ones are constant potential generators. They have a lot less ripple effect than anything else, right? So they're giving us a really high quality X-ray. It is very, very important to plug these things in after every use, right? Because just like the reason I still got my iPhone 5 is I plug it in a lot, right? I baby the hell out of the battery on this thing. And some of that comes from working with portable X-ray machines for so long. You do not know how crappy your day can get as an X-ray tech until you have a portable machine lose power on you in the middle of the OR. That's a bad day. That's a really bad day. Because those things weigh at least a ton, and it ain't going anywhere, right? So we're talking about running extension cords to the OR to charge up this stupid machine to get it out of there, past sterile fields and everything. That's a bad day. So after that, charge it up after every use, right? The batteries will love you for it. That's on page 671. It says the batteries will love you and be at your wedding in the book. No, that's my translation. The other thing, distance considerations. I've got this little thing. This is your best friend, right? I know that your markers are cool, but this is the thing that you need to get after the marker. This little like Taylor measuring tape. I love this thing. Why? Because I can measure distances with it. No, I've not been carrying it much, but I'm going to start carrying it more because it makes me feel better about life. I would encourage you, guess what? They are required for image production 1 and 2. So go ahead and buy yours now. You can get them for like $3 on Amazon. Make sure that it can measure at least 50 inches. That. All right. And that's on page 627. Buy one of these things. Top of the page, second column, it says if a measuring tape is attached to the radiographer, if a measuring tape is attached to the tube or the collimator, it should be used. The radiographer may wish to carry a compact tape measure in a pocket. It's a good book.
That's a good book.
That might be on my tombstone.
You want to be buried with your
My markers.
markers and your measuring tape?
Choking up a little bit.
Mitty, King Cotton, Roberts.
Buried missing his left marker. Ow, Nick. Okay. Last thing that I'll say about ports is the CR, the central ring, needs to be perpendicular to the anatomy. So he illustrates that with this crash test dummy on page 673. I don't know what's going on in that picture. But what it is trying to point out is that it's important to keep the central ray perpendicular to the anatomy rather than cassette if one must choose. Tapping the book at you. All right.
So when your texts say perpendicular to the IR,
You can tell them, not according to my textbook. And throw the book at them.
and so do they.
And then snap this at them. Be like,
I don't have the body strength to throw that book.
Enter the dragon. All right. Other considerations, last thing is low ratio grids are going to be your best friend for portables, so 5x1 to 6x1s, but we've not talked about grids yet, so whatever. Grid software is probably going to be making grids obsolete in the next 5 years or so. He talks about that on page 674. I agree with him on that, and he presented on it recently. And then finally, this is the reason I'm stressing this, is technique charts are machine specific. It needs to be stuck on the machine somewhere. Now some of them are like calculated and stuck into the computer or whatever, like Tesla-esque laptop type thing. I don't know, it kind of makes me disgusted with these like iPads and things with the machines. Yeah, X-ray techs don't need iPads. I mean, I like my iPad, but no, there needs to be a technique chart specific to that machine somewhere on the machine. That's the point of that. All right. Last thing, it's not in the book, tomography. This is not talking about computed tomography. This is talking about moving the tube, the patient, or the image receptor during exposure. What they do in the dentist office is tomography, right? This blurs out superimposing structures above and below the plane of interest, right? So we talked about anatomy of interest, talked about tissue of interest. Now we're talking about the plane of interest. Yes. The main place that this was used on back in the day was the kidneys, because the kidneys are retroperitoneal and they've got a lot of stuff obscuring them. So on a KUB, they are hard to see, right? We've all tried to find kidneys on a KUB and we can't. Using tomography, you can, because you can set the fulcrum, the part that's not moving, at the level or the plane of the kidneys, right? So by doing a simple measurement on the patient's side, using calipers or one of these, right? You could estimate the plane in which the kidneys are lying and blur everything else out. So all I see is the plane where the kidneys live. I don't see any other plane, just the plane where the kidneys live, not airplane. So it blurs out superimposing structures above and below the plane of interest. Why? Because we're moving it. I'm moving the tube and I'm moving the image receptor as I make a picture, And the only thing that's not blurring is the fulcrum. The area in the middle doesn't move. So you set that fulcrum at the place you don't want to move, everything else is blurred out. That is tomography, right? So the anatomy of interest is set at the fulcrum, the point of no movement. It gives you the sharpest resolution. It's on page 643 in the textbook if you need an illustration. I know, I didn't assign this as reading because this is brutally boring stuff. So y'all are already complaining enough about the assigned reading for this class. Trying to simplify your life and mine. Yes, see how that is. So, page 643. 43, I lied, it's not that page. I'll find it.
What does lossy mean? I see it in the textbook, and I asked my tech the other day why it was on her picture. Like, right at the bottom, it says lossy.
Lossy on her paycheck?
No, on our picture, on our image.
Oh, on the picture. Oh, lossy means that the image is not as high resolution as what was actually captured. So it's how it's archived. It's archived in a lossy way, and if you wait, it will gain more resolution. Digital imaging. We will talk about it. Good question, though, but not necessarily related to this. So the exposure arc is the angle. The greater the arc, the thinner the slice. Right? The greater the arc, the thinner the slice. And don't worry about amplitude. All I want you to know is that tomography blurs out stuff above and below the plane of interest, and you're good to go. Okay? We good with that? You'll learn the actual techniques if you're at Memphis whenever they're doing a tomography, which is pretty much never. Why? Because we have computed tomography and dental hygiene. All right.